Hello and welcome to this short video on the golden ratio. The golden ratio, often written as this character or this character, pronounced as phi, not phi. This is not pronounced as phi, this is pronounced as phi, is a number, and this number is approximately equal to 1.618. We will see how we derive this number and what this number is and what its importance is, specialness is, and why there's so much hype about it in this video. So the golden ratio, how is it defined? Consider a line like this. Line like this which has two segments. Here I have marked segment A and segment B. Segment A is in red, segment B is in blue. We are assuming that A is greater than B, the length of A is greater than B, and that A and B are both positive lengths, because of course if you have a length it has to be positive. So here what we want to consider is the ratio of A to B. The ratio of A divided by B. When this ratio of A, the longer side, to B, the shorter side, is equal to the ratio of the total length of the line segment to the ratio of the longer side A, i.e. this is equal to the value of A plus B divided by A. When this condition is satisfied, then this ratio is going to be equal to the golden ratio. So let me say it again. When the ratio of the long side to the short side is equal to the ratio of the total length of the line segment to the long side, i.e. A divided by B is equal to A plus B divided by A, when this happens, the resulting ratio is what we call the golden ratio. So here you can see we have actually two equations. We have one equation that when these conditions are met, when A and B are such that their ratio is the golden ratio, A divided by B is equal to the golden ratio, and as well A plus B divided by A is also equal to the golden ratio. These two equations can actually be used to find the exact value of the golden ratio. From the second equation we can see, taking this A divided by A out as its own 1 as 1 outside, we have 1 plus, and then what's left is B divided by A, so we have 1 plus B divided by A is equal to the golden ratio of 5. Over here from the first equation we can see that if A divided by B is equal to the golden ratio, then B divided by A is equal to 1 divided by the golden ratio. So we can call this equation 1 and equation 2. We can see that we can substitute 1 into 2 because over here in number 2 we have B divided by A. Doing that, what we get is 1 plus 1 divided by phi is equal to 5. So 1 plus 1 divided by the golden ratio is equal to the golden ratio. From this, if we multiply both sides by the golden ratio here, we can see on the left we get the golden ratio plus 1 is equal to, on the right side we get the golden ratio squared. Rearranging a little bit more, we can see that the golden ratio squared minus the golden ratio minus 1 is equal to 0. This is a quadratic equation. We know how to solve quadratic equations. If you don't know, check this video right here. So over here we can directly substitute the values A, B and C and find what the value of the golden ratio is. According to this, the golden ratio is going to be equal to negative B, which is negative 1, so positive 1, plus or minus the square root of B squared, which is negative 1 squared, which is 1, minus 4AC, minus 4 times A is in this case 1, and C is also negative 1, so times negative 1, all divided by 2A. A is 1, so 2A is also going to be 2. So we have this. So therefore the golden ratio is going to be equal to 1 plus or minus the square root of, inside here we have 1 minus 4 times minus 1. So minus 4 times minus 1 is plus 4. Plus 4 plus another 1 is plus a total 5. So we have 1 plus or minus the square root of 5 all divided by 2. Now here, since we were dealing with positive lengths A and B, our final answer needs to be a positive number. Since root 5 is going to be greater than 1, if we do 1 minus root 5 is going to be a negative number. Since the golden ratio cannot be a negative number, the positive number solution must be the correct one. So therefore, the golden ratio of 5 is equal to 1 plus the square root of 5 divided by 2. This is the exact value of the golden ratio. And you might be thinking at this point, alright, that's cool, but what is it good for? Why do we like it? Why is it so exaggerated in different places, and why is every recreational mathematician talking about it at some point in time? There's multiple reasons for this. One reason is that it is a very nice ratio. By very nice, I mean it is artistically pleasing, and at least people in the Renaissance times thought so and thought it was nice. Even further back, it has been studied by the ancient Greeks and such, but it gained a particular popularity, let's say, during Renaissance times. It can be seen in many places, in many different paintings, which I'll flash a bunch of them on the screen here, where you can see the golden ratio in action. And it can also be seen in architecture. I'll also flash that on the screen, few images. And it can also be seen in nature. So here's an example that you yourself can check out. Take your hand and measure the length from your elbow up to your wrist, and then your wrist up to the tip of your finger. If you measure these two lengths, like this length from here all the way up to about here, and then you measure the length from here all the way up to about here, you can see that this ratio is also approximately equal to the golden ratio. If you take the total length of your hand and then you consider this total length relative to this, or you consider the total length relative to the red line, or the red line relative to the blue line, you will see that you have approximately the golden ratio. Now it could be a little bit up and down, of course, everyone's proportions are not perfect, but this will generally be able, you will generally be able to observe this ratio in your body. So now then, let's look at some other places where the golden ratio appears to show up. One common example that most people know is something called the Fibonacci sequence. If you don't know the Fibonacci sequence, well, it goes like this. Let me just write this guy's name, Fibonacci sequence. It goes like this. You start with 1, and then the next term is 1. The next term after that is 2, and then you go 3, and then you go 5, and then you go 8, and then you go 13, and then you go 21, and then you go all the way up to 34, then you go 55. Some of you might see the pattern, some of you might already, of course, know the pattern, but some of you might not. The pattern of this sequence is this. If this is term 0, which is often written with a sub notation, so f sub 0, this is term 1 or f sub 1, then any f sub n, actually we'll write it like this, n plus 2 is equal to the previous term f sub n plus 1 plus the previous term before that, which is f sub n. So here this term is f sub 2. F sub 2 is going to be f sub 1 plus f sub 0. So you add the previous two terms to get the next term. So here 1 plus 1 gets us to 2. And then for the next term, f sub 3, to get f sub 3, what you need to do is take the last two terms, which is f sub 2 and f sub 1, and add them together. So then we get 1 plus 2, which is equal to 3. The next term after that is 2 plus 3, which is equal to 5. Next term after that is 3 plus 5, which is equal to 8. 2 plus 3, which is equal to 5, and then 3 plus 5, which is equal to 8. The next term after that is 5 plus 8, which is equal to 13. The next term after that is 8 plus 13, which is equal to 21. And then 13 plus 21, which is equal to 34. 21 plus 34, which is equal to 55. And you can carry on. This sequence here is ever growing, but you might be surprised, or some of you might of course not be surprised, to find that the golden ratio can be found within this sequence. How do you find it? Well, as we get larger and larger terms here, the ratio of each consecutive term is going to be approaching the golden ratio. 55 divided by 34 is close to the golden ratio. The next term after this is going to be 89. 89 divided by 55 is going to be approximately the golden ratio. As you get further and further right, this approximation gets better and better. Why does this happen? Well, we can just kind of think that if there is some constant ratio, it should be something like this. There should be some ratio r here, there should be same ratio here, there should be same ratio here. So then if we consider any term and call this term alpha, then the next term after that, if there was a common ratio, would be r times alpha. And the next term after that would be r times alpha, or r squared times alpha. If there was a common ratio, we are just making an assumption here that if there was a common ratio, then this would be the relationship. So considering any three consecutive terms like this, since any fn plus 2 term is the sum of the previous two terms, here the f sub n plus 2 term r squared alpha should be equal to the sum of the previous two terms, which is going to be r alpha plus alpha. Dividing everything by alpha here, we see that r squared must be equal to r plus 1. And then we get r squared is equal to, actually we'll take the other side, r squared minus r minus 1 is equal to 0. This is exactly the equation that we use to find the golden ratio up here. So what does this mean? This means that if there was a ratio, that ratio would have to be the golden ratio. So therefore this r would have to be 1 plus root 5 divided by 2. Another place where you will often see the golden ratio is in pentagons. So now let's explore where we can find the golden ratio within pentagons, and this also relates to the sine of 18 degrees and the cosine of 36 degrees. Let's now see where these things come in and where these things are related to pentagons. So here I have drawn a regular pentagon, and what I'm going to do next is draw all of the diagonals of this pentagon. By diagonals, what I mean are the lines like this, going from one corner of a pentagon to the other corners of the pentagon. So going like this to here, going from this corner to here, and same thing with this corner. I'm going to go to this top point here and this point here, and finally this last diagonal which I'm going to draw is going to be like this. So now we are pretty much done with our construction, and all we have to do now is draw out some angles in order to find the golden ratio within this triangle. So here I'm going to start labeling these points. Let's say we label this point down in the bottom right as A. Then the next point here will be B. This point will be C. This point will be D. And this point will be E. Let's also label the internal intersections of these things. So internally there's an intersection here, there's an intersection here, intersection here, intersection here, and an intersection here. We're going to start labeling these as P, let's say Q, R, SNT. So here, let's suppose that this is a regular pentagon with a side length of 1. So therefore the external side length here is 1, which means all of these side lengths are of length 1. So all of these lengths are equal. I just put a little few lines here to indicate that all these lengths are equal, and each of these lengths is of length 1. So now let's start making some observations. The first thing we know about a pentagon is its internal angle. We know that the external angle here needs to be a total of 360 divided by 5. So here this angle needs to be 360 divided by 5, or 72, meaning that the rest of this angle on the inside here is 180 degrees minus that angle. Here we have 72 degrees. 180 degrees minus 72 is going to be 108 degrees. So this whole angle here, I'm going to actually draw it a little bit smaller. This whole angle here is 108 degrees total. This is 108 degrees total. Next, let's start considering some other angles within this thing here. So here, considering the triangle BCD, we have an isosceles triangle since this leg and this length are both equal in length. One of the angles is 108 degrees, so therefore this angle and this angle have to be equal to each other. This angle and this angle have to be equal to each other, and the total sum of the three angles needs to be 180 degrees. The angles left over when we remove this 108 degree angle is 72 degrees. So therefore this 72 needs to be equally divided between this angle here and this angle here. Therefore each of these angles is 72 divided by 2, or 36 degrees. So therefore this is 36 degrees and this is 36 degrees. Furthermore, by symmetry we can see, since the same thing should apply to the triangle ABC, this angle should be 36, but more importantly this angle should be 36. Similarly, this thing should also apply to the triangle CDE, meaning that this angle is 36 and this angle down here is 36. Furthermore, what this means is that since the total angle here is 108 degrees, when we remove 2 36s, what we are left with over here is 108 degrees minus 36, which is also 36 degrees, because 36 times 3 is 108 degrees. And then we can also see here this angle here is 72 degrees, this is also 72. Again, by the same logic as this is isosceles triangle here, these two lengths are equal to each other. And furthermore, the total angle needs to be 180 degrees. 180 minus 36 gives us 2 times 72, so each of these angles must be 72 degrees. This is all we need to now start considering different lengths and start to identify where the golden ratio is coming from within this triangle, within these triangles. So first off, I want you to make an observation about this angle here, and the triangle BCR. Considering triangle BCR, tell me what you see. Well, over here we have 72 degrees total, 36 plus 36 is 72. This angle is also 72. So therefore this triangle must be isosceles. If this triangle is isosceles, then the two corresponding side lengths BC and BR must be equal. So we can see on the corner here, BC must be equal to BR. So now, if BC is equal to BR, that means that the length BR must be equal to the length BC. The length BC is 1. Therefore, the length here BR is also equal to 1. So therefore, BR is equal to 1. Now, I want to direct your attention to what's left over of the side BD. Of the length BC, when we remove 1, we are left with some other length. Let's say this length is delta. So we'll say let the length RD equal delta. By symmetry, this other side is also equal to delta. So therefore, this other length BQ is also going to be equal to delta. So we have here this length delta and this length also delta. This length is the total length here minus minus a delta minus another delta. We'll ignore that for now, that's not relevant. What we care about is that this length is delta and similarly this length is delta. Now directing your attention to BQC, in this triangle, this angle here is 36 degrees. This angle here is also 36 degrees. So therefore BQC is also an isosceles triangle. Again, if BQC is an isosceles triangle, then the corresponding side length must also be equal. If BQ is then equal to CQ, this means that CQ itself is also going to be a length of delta. So now, what I'm going to do next is direct your attention to the triangles BCD and BQC. So here, this angle here is 72 and then 180 minus 72, which is 108 degrees. Directing your attention to these two triangles, if I extract them and draw them separately, the first triangle BCD is like this. If I draw it out separately outside of this, outside of the mess of shapes we have here, the BCD triangle looks like this. So writing its coordinates, we have B, C and D here. So therefore the points here are B here, a C here and a D here. Writing out the angles here are 36 degrees and at C 108 degrees. So here we have 36 degrees, over here we have 36 degrees and over here we have 108 degrees. As for the lengths, BC and CD are both equal to length 1. And the length BD, which we defined this length to be delta, is now this length 1 plus this length delta. So therefore, the length BD is equal to 1 plus delta. Now let's also extract this other triangle BQC. Before extracting it, I'm going to do one more thing. I want you to do this in your head. Rotate this triangle until this side is flat. When you do that, and then you bring that triangle out here, what we will get is a triangle that looks like this. It's going to be like this. Certain length up, certain length down. If you write the points here, this point here, this point here B is going to be the point in the bottom left. So that's going to be this point here. This point is B here. And then when you rotate it, that apex is going to be Q. So the top is going to be Q. And the other point is going to be C. So we have Q here, C here. This triangle is exactly this triangle here. We just extracted it out of this mess of shapes. How about the angles? Well, this is 36 degrees, this is 36 degrees, and at Q we have 108 degrees. So drawing that in down here, we have 108 degrees here, 36 degrees here, and 36 degrees here, 36 degrees here. How about side lengths? Well, BC is of length 1, writing that down, this is of length 1. And the rest of them, well, BQ was equal to DR by symmetry, so BQ is equal to delta, and similarly CQ is equal to delta. So therefore these two side lengths are both delta. Now consider the two triangles we have before us. Both of these triangles, as you can clearly see, have the same set of angles. this angle is 108 degrees, the other two angles are both 36 degrees each. So therefore this is not congruence, but this is something that we call similar triangles. The triangles BCD and the triangles BQC are similar to each other. Similar triangles have the property that if you scale all the side lengths up by a certain scaling factor, you can go from one triangle to another. So there is some common ratio here where we can multiply each side length by in order to get from the left triangle to the right triangle and vice versa. So we can get from the left triangle to the right triangle and the right triangle to the left triangle by multiplying or dividing by some ratio which I am going to label as k. So if this is the case, then if we have to multiply, let's just suppose that since of course here this triangle is smaller than this triangle, let's suppose to get from the left to the right to the left, we need to multiply by k. So let's represent that as multiplication by k to go from the right triangle to the left triangle. Considering the multiplications we do, this side length is correspondent with this side length, which means in order to get to here, we need to multiply delta by k. So then delta multiplied by k is equal to the corresponding side length, which is 1. So delta multiplied by k is equal to 1. And this equation gives us that k is equal to 1 divided by delta. This is equation 1. If instead we compare the other two side lengths, that's in this side length and this side length, then we can see when we scale 1 up by a factor of k, we need to get a length of delta plus 1. So here we can say that 1 scaled up by k must be equal to delta plus 1, meaning that k is equal to delta plus 1 divided by 1. Now, look at these two equations. See anything familiar? Well, of course you do. Over here we can see right here k is equal to delta plus 1 and delta is 1 divided by k from this first equation. So we have that k is equal to 1 divided by k plus 1, meaning that k squared is equal to 1 plus k, meaning that k squared minus k minus 1 is equal to 0, meaning that k is in fact equal to the golden ratio 5. So there we go. We have found the golden ratio hiding inside of the pentagon. So now we can use this value, and in fact here what this means, what the ratio here means is that 1 plus delta is now going to be equal to the golden ratio, because here we saw k was equal to 1 plus delta, k is equal to the golden ratio. So therefore this length here 1 plus delta is equal to the golden ratio 5. So here this is equal to 5, meaning that within this triangle we can now say that BD length is equal to 5. In fact, because of symmetry, every single diagonal within a pentagon, a regular pentagon, is equal to the length of the golden ratio provided that the side length is 1. Or you could say the side length to a diagonal ratio of a regular pentagon is equal to the golden ratio. So once again we have found the golden ratio. How does this relate to the sine of 18 degrees and the cosine of 36 degrees? Well, again, taking this triangle, we can actually see that. If I extract this triangle, let's say we'll take it to the next page. We'll scale it up a little bit so we can easily see things. If we scale it up to, let's say, this size and draw out the side lengths we have these two base angles are going to be 36 degrees each. So this is 36 degrees. This is 36 degrees here, as well as this angle here. These are both 36 degrees, not 30 degrees, 36 degrees. And the apex angle is going to be 108 degrees. As for side lengths, taking this thing, we had 1 and the golden ratio. So here, over here in this triangle, this hypotenuse is 1, this is 1, and this is the golden ratio total length. So now, I actually prematurely said hypotenuse because I didn't actually say where we're getting the hypotenuse. If we divide this triangle in half like so, such that this line is perpendicular to the line of the base here. I'll actually put the symbols here, BCD. If we construct this line here, then since the total length BD is going to be the golden ratio and this line perfectly divides BD in 2, each of these line segments is going to be the golden ratio divided by 2. So this length is the golden ratio divided by 2 and this length is the golden ratio divided by 2 up to this point. So now within this triangle we can see, considering the cosine of 36 degrees, the cosine of 36 degrees is equal to the adjacent divided by the hypotenuse. The adjacent here is the golden ratio divided by 2. So golden ratio divided by 2 divided by the hypotenuse, which is 1. So then we have that the cosine of 36 degrees is equal to the golden ratio divided by 2. So there we go. The cosine of 36 degrees is related to the golden ratio. In fact, because the cosine and sine are related by this expression, that the sine of pi by 2 or 90 degrees minus the angle theta is equal to the cosine of that angle, or similarly the cosine of pi by 2 minus an angle is equal to the sine of that angle, we can say by this that the sine of 54 degrees is also equal to the golden ratio divided by 2, because 54 is 90 degrees minus 36 degrees, or as in this angle in radians would be pi by 2 minus this angle in radians. 36 degrees in radians is 180, 36 is 180 divided by 5, 180 in radians is pi radians, so therefore 36 degrees is equivalent to pi divided by 5 radians. We have this relation, so therefore the cosine of pi by 5 radians is equal to the golden ratio divided by 2. Similarly, the sine of this angle, which is pi by 2 minus pi by 5, which if I simplify in terms of fractions, pi by 2 minus pi by 5, is equal to 5 pi minus 2 pi divided by 10, or 3 pi by 10. So therefore the angle, the sine of 3 pi by 10 radians is also equal to the golden ratio divided by 2. What about the sine of 18 degrees like I alluded to earlier? Well, that we can also do using the same triangle, but we have to do a different observation in order to get that. Over here, if we consider this setup that we have here, and instead of considering the total triangle BCD, if we instead consider this internal triangle R, Q and C, so QCR triangle, and extract that one out, we can see this. If I extract that triangle out separately, we'll give a little spacing here for the other triangle. Extracting the triangle RQC out, it will look something like this. At the apex, if you go up, you can see here we have Q, here we have R, here we have C. This angle total was 36 degrees and the other two were 72 degrees each. So this is 72 degrees, this is 72 degrees. If we look at the side lengths, what we have here is a side length here of delta. What is delta? Well, going up over here to this relationship, actually down here to this relationship, 1 divided by delta is equal to k, and k is equal to the golden ratio. So therefore delta is equal to 1 divided by k, or 1 divided by the golden ratio. So therefore this side length here, delta, is equal to 1 divided by the golden ratio. And drawing that down here, we have over here these two side lengths are 1 divided by the golden ratio. This is 1 divided by the golden ratio, this is 1 divided by the golden ratio. What about this base here? Well, over here, if we look at this thing, what we have here is that the total length here is 1 plus delta, or the golden ratio, and here we have two deltas, one here, one here. Subtracting the two deltas from the golden ratio, we get the internal part here. So the internal part here is the total length, which is the golden ratio, minus 2 delta. So the golden ratio minus 2 delta, and we know delta is 1 divided by phi. So therefore this length is going to be the golden ratio minus 2 times 1 divided by the golden ratio. So now if we consider dropping a perpendicular down from C once again, we can see this. This angle right here is 18 degrees because we are bisecting the angle. Here we have 18 degrees. What we have here is half of this total length here. If I half this thing, what we get is phi divided by 2 minus 1 divided by phi. So writing that down, if I instead simplify this and write here phi on 2 minus 1 on phi. Similarly here this side length is phi on 2 minus 1 on phi. So therefore in here in this triangle, the sine of 18 degrees is equal to the opposite divided by the hypotenuse. So here the opposite here is phi on 2, so phi on 2 minus 1 on phi divided by the hypotenuse, which is 1 on phi. So now dividing by 1 on phi is the same as multiplying by phi. So if we do that, we have phi by 2 minus 1 on phi multiplied by phi. Cutting this to this, we get minus 1 here, and multiplying these two, we get phi squared here. So we have over here a phi squared divided by 2 minus 1. This is what we get. So now taking 2 as the common denominator here, we can see what we have is phi squared minus 1 times 2 divided by 2. This is what we have to try and evaluate. This is the sine of 18 degrees. Now we could leave it like this, but we can actually simplify it due to the relationship of the golden ratio. Recall that the golden ratio squared, k squared, is equal to 1 plus k. We can use that identity here. Down here, the golden ratio squared is equal to 1 plus the golden ratio. Substituting that into here, if we take this to the next page, the sine of 18 degrees is equal to phi squared minus 2 on 2. Substituting phi squared as 1 plus phi, we have 1 plus phi minus 2 divided by 2, which we can then simplify to phi minus 1 divided by 2. Now this is again a place that we could stop, but we can actually simplify this even further. You might not believe me, but we can. Over here we can see phi squared is equal to 1 plus phi, meaning that phi is equal to 1 plus 1 divided by phi. This was one of the identity equations that we had with the golden ratio. Here we can actually substitute this thing into here. We can substitute instead of the golden ratio 1 plus 1 divided by golden ratio. Substituting that in, what we have is 1 plus 1 divided by the golden ratio minus 1 divided by 2. This is actually the final form that we give it. Cancelling these plus 1 and minus 1, what we have left is that we have 1 divided by the golden ratio divided by 2. So we have 1 divided by 2 times the golden ratio. This is actually where we usually end this thing and write that the sine of 18 degrees is equal to 1 divided by 2 times the golden ratio. As in the sine of the angle 18 degrees, which is pi by 10 radians, so sine of pi by 10 is equal to 1 divided by 2 times the golden ratio. Due to the symmetry of sine and cosine, the cosine of 72 degrees is equal to the same exact thing. The cosine of 72 degrees is also equal to the 1 divided by 2 times the golden ratio. Or if you write this in radians, the cosine of 4 over 10 or 2 over 5, we'll write that simplification, 2 pi divided by 5 radians is equal to 1 divided by 2 times the golden ratio. So again, once again, we have related these angles to the golden ratio. The sine of 18 degrees and likewise the cosine of 72 degrees is 1 divided by 2 times the golden ratio. And the cosine of 36 degrees or the sine of 54 degrees is equal to the golden ratio divided by 2. Marvelous. We have golden ratio in trigonometry as well. So as a final part to this video, I'm going to be showing you how you yourself can construct the golden ratio. So here what I've drawn is a square of side length 1. So this is 1, this is 1, this is 1, and this base is also 1. So using this square, we're going to be constructing the length that is the golden ratio. So here we have A, B, C, D. Let's just mark these points, A, B, C, and this point is D. To construct the golden ratio, what we're going to do is first find the midpoint of any of the sides here that are drawn. I'm going to find the midpoint of the side AD. If you're using a compass and a ruler, of course, you can do this by taking the point D, drawing an arc above and below the line, and then doing the same thing with the point A, drawing an arc above and below the line, and then cutting the two in order to find the midpoint. So if you found the midpoint like that, now you have the midpoint. Now what I want you to do is to draw the line from this midpoint to one of the corners of the top of the square like this. What we are doing here is to try to construct the square root of 5, because the square root of 5 is essential in order to find the golden ratio. So over here, when we bisected this AD length, the total AD length was 1. So therefore each of these lengths is now a half. This is a half and this is a half. Let's call this new point we formed E. So within this triangle, we can see there's a 90-degree angle here. We have a half here and 1 here. So therefore Pythagorean theorem applies, and this hypotenuse squared is equal to this squared plus this squared. So therefore the hypotenuse is equal to the square root of 1 squared plus 1/2 squared, which is the square root of 1 plus the square root of the square of 1/2 is 1/4, so 1 plus 1/4, which is, if we add them together, 5 on 4. Taking the 4 out of the square root, we can see this is the square root of 5 divided by 2. So therefore this hypotenuse here is the square root of 5 over 2. Now the next step we want to do here is take a compass and use this diagonal length that we've drawn here as our radius. So we're going to make a compass. We're going to take this compass, move it to this point E here, center it at the point E, and then slowly scale it up until we reach this, and then we're going to draw an arc with the point E as the center from the point B down to the side length extended of AD. So we're going to do this. Drawing this arc down to here, we can see it cuts at some point. We're going to label that point, this point here, we're going to call this, let's say, F, and now the distance DF that we have here is equal to the golden ratio. How? Well, this length was root 5, and since we are using a radius of a circle, this length here, EF, is also root 5, so divide by 2. So this length here is the square root of 5 over 2. So now if we consider the total length DF, DF is equal to this length here, which is 1/2, plus the length EF, which is root 5 on 2. So we have 1/2 plus root 5 on 2, root 5 on 2, which is 1 plus root 5 on 2, which is exactly the golden ratio. So there we have now successfully constructed the golden ratio. Often you don't see this alone. Most of the time when people do this, they tend to do a little bit of a recursion, and I'll show you that recursion as well. Over here, when they obtain this point, what people tend to do, and this you will probably seen this often, it's called the golden spiral. You definitely have seen this. This is not, by the way, this construction we're going to make is not exactly the golden spiral. It is rather an approximation. So drawing this thing, what we do is extend the other top side length CB, and then draw a vertical from the point F upward until it reaches this extended side length here. And then the next thing we do is take this length AF, which, if you don't know what AF is, just look at the thing. This whole total length is the golden ratio. The length AD is equal to 1. So therefore this length AF is the golden ratio minus 1. What we do here is now construct a square in this small rectangle that we have here. Within this rectangle we draw a square which has side lengths of the golden ratio minus 1. So doing that, we have, it's about here. So drawing the square in, now we have that this side length is the golden ratio minus 1, and all of these side lengths are equal. So now what I want you to do is consider this side length here. The total length here is 1, so this top length is 1. Since this was the golden ratio minus 1, this length here must also be the golden ratio minus 1. So I'm going to mark that as the golden ratio minus 1. The total length here is the height of this square here, which is 1. So therefore, if this is 1 and this is the golden ratio minus 1, what's left over is 1 minus the golden ratio minus 1. If we take the minus to the inside, we have minus golden ratio and a minus minus 1, so which is a plus 1. So then we have 1 plus 1 minus the golden ratio. So this is equal to 2 minus the golden ratio. So now what I want to do is direct your attention to this rectangle here. This small rectangle here is actually self-similar to this larger rectangle here. It also has the ratio of 1 to the golden ratio within its side lengths. To prove that, what I'm going to do is to take this length, divide them, and show you that we do in fact get the golden ratio. So what I'm claiming is that this long length here, which is phi minus 1, is divided by this length here, which is 2 minus phi, is equal to the golden ratio. So let's evaluate that value. What we have is phi minus 1 divided by 2 minus phi, and I'm claiming that this length is equal to the golden ratio. So in order to simplify this, what I'm going to do is use some identities that we know. One identity that we know is that the golden ratio squared is equal to 1 plus the golden ratio. Another thing we know is that the golden ratio is equal to 1 plus 1 divided by the golden ratio. I'm going to take the second one, which is obtained from the first one. The second one I'm going to take, and I'm going to take this 1 to the other side. So what I have then is that 1 divided by the golden ratio is equal to the golden ratio minus 1. We are going to be using this. Over here we can see on top we have the golden ratio minus 1. On the bottom, if I take one of the 1's out of this 2, I can have 1 plus 1 minus the golden ratio. So here I can replace some of these with this identity here. Over here, the golden ratio minus 1 is going to be equal to 1 divided by the golden ratio, and on the bottom here, 1 plus the 1 minus the golden ratio is going to be 1 plus the negative 1 divided by golden ratio, because if golden ratio minus 1 is going to be equal to 1 divided by the golden ratio, then 1 minus the golden ratio is going to be negative 1 divided by the golden ratio. This is actually negative 1 over the golden ratio. So now I'm going to multiply the top and bottom by the golden ratio. Doing that, I get on the top we have the golden ratio times 1 divided by the golden ratio, which is just 1. On the bottom we have the golden ratio minus 1. The golden ratio minus 1 is equal to 1 divided by the golden ratio. So what we have here is 1 divided by the golden ratio, which is then equal to the golden ratio. Hence we have shown that within this smaller rectangle that we have constructed here, we have the same side length ratio of 1 to the golden ratio. So this side length here, this base length here, divided by this length here is also equal to the golden ratio. And then what you do is simply repeat this process again. Taking this new rectangle that we've drawn here, which has the ratios of the golden ratio, the next thing you're going to do is take it within this rectangle, again mark out a square. So here we have this length here, which is 2 minus the golden ratio. Mark out a square which is of side length 2 minus the golden ratio, and then do this same process again. Cut out another square like this, and then here it doesn't really look like it, but if I kind of make it look nice, this internal rectangle here is also going to be a golden rectangle, meaning that this side length to this side length ratio is going to be equal to the golden ratio. So now you know, repeating this process, you yourself can also construct the golden ratio and construct what we call the golden spiral. You've of course always seen images of this thing, but maybe until now you might have not known what it is. This is what it is, and if I continue this process, you can see we get that familiar shape, which is what we know as the golden spiral. It looks like this, and what we would do then is draw the arcs from the center outward. So what you do, draw the arcs like this. I'll actually erase these old construction arcs that we did earlier to draw the thing that most people often see when they think about the golden ratio, which is this concentric rectangle and square thing. It looks like this. You draw like this, this arc, and then you draw this arc here, this arc here, and this arc here. This is what most people think about when they think about the golden ratio. And yes, it is the golden ratio, but this is kind of like an artistic depiction of the golden ratio. Mathematicians think of the golden ratio not like this, but rather as the value such that the value is equal to 1 plus 1 divided by that value. Or you might think of it as, given us a segment of a line like this, if we have A and B, then the golden ratio is the ratio such that if A divided by B is equal to the golden ratio, then that is also equal to A plus B divided by A. I could go on and on for hours about the golden ratio, different places where we find it, different interesting places where it appears, where it becomes useful, but for now we're going to end it there. So this is the golden ratio. This is what it's all about. There are multiple other places where it shows up, but we're going to end this video here. So thank you for watching this video, and goodbye.